Okay, so just doing a test here. So this is the second lecture video for Thursday, February 13th. So last time, when we were ending with the end of the lecture 5, we were seeing how we could use the normal distribution to determine the probability of some event, right? If we can assume that we're dealing with a data set that follows a normal distribution, we can make a lot of assumptions in terms of figuring out the probability of randomly choosing a certain value, right, from that normal distribution, right? With, of course, the greatest probability being choosing randomly a value that's nearer to the mean, and lower probabilities for choosing values further away from the mean, whether that be values higher or values lower. So most of basic probability lecture 5 dealt with those three distributions: the Poisson, the binomial, which are discrete distributions, and then we did that normal distribution on part 2 of the last video. So this is new material, and this is material, I should say, that will not be on the midterm on the 27th, okay? So again, everything up to the end of probability lecture 5, part 2 will be on the exam. And like I said before, the practice lecture exam will be opening later on today. So you can take a look at that. So starting with lecture 6, I'll maximize things here. So as I said, we were looking at how we could use the normal distribution to figure out probability of randomly choosing a certain value from that distribution. But how do we know that our data set is following a normal distribution? That'll be a big part of this first lecture, of lecture 6, will be how to figure out whether the data set that we have in front of us is actually sufficiently following a normal distribution or not. If it's not, right, we cannot make those assumptions and figure out probability and things like that. And then the second part of this first part of lecture 6 will be looking at inferential stats. So we'll be moving away from the descriptive statistics, which we've been doing so far, central tendency, dispersion, different metrics to basically characterize where our data set is, right? We're going to be moving into inferential stats, which is essentially taking a sample and trying to infer, hence the name inferential, basically trying to characterize the larger population just from what we see in that sample. And associated with that will be things like standard error of the mean, sampling error, and sampling methods into part 2 of lecture 6. Okay, right, so just kind of recap, right? Last time we're dealing with the normal distribution. So the first part of this lecture is going to be, how do we know that the data that we're looking at is following a normal distribution? And what are some of the different ways that we can see if our data is actually a normal distribution or not? How do we test our data set for normality? Well, the first thing we can do, and we've done this a little bit already in the labs and the lectures, is just to look at the data, right? We can make a whole bunch of different plots to visualize our data, whether those be histograms or box plots, right? So we can make a histogram like this, and just by looking at it, we can get an idea in general whether we're dealing with a normal distribution, because remember, our normal distribution is going to be a unimodal symmetrical distribution, right? So if we see two modes, we know we're not dealing with a normal distribution. If it's fairly heavily skewed either way, we know that's probably less likely to be normally distributed, things like that. So just by looking at the graphics, right? So here's another histogram, right? Just showing the frequency of these different datas here. So we have some data here that's the units milligrams per kilogram, right? So the amount of nickel in maybe some sample of dirt, right? So here we have our histogram with our basically kind of like our columns there. And then we've run a best fit line through it. And we're comparing that to the red, which is what we would expect for a normal distribution. So in this case, in this example, we can see that our data set is closely following a normal distribution. It's not quite perfect, but it's close. So this is the first way that we can check whether we're dealing with a normal distribution, is just by visualizing it, looking at it. So how does our data set not follow a normal distribution? Well, there's two main ways, right? Well, I guess three. First one, like I just mentioned, is that we have more than one mode, right? If we have more than one mode, we definitely know that our data set's not following a normal distribution. The other two main ways is that our data set is either too skewed, either positive or negative, or its kurtosis is off. It has too high of a positive kurtosis, meaning that's too peaked, or it's too flat, platykurtic. Okay, so those are the two other main ways in which our data set will deviate from a normal distribution. So in the Moodle lecture folder, I put an Excel file, lecture 6, heights normal distribution, in which I have 3 columns, right? And the first column, these are 100 heights for each of these columns in centimeters. Those are the units. And so in the first column, I have a data set of observed heights of 100 people, okay? The second column, I basically constructed the heights that follow perfectly a perfect normal distribution. So that's what we would expect, this second column here, if these heights were following a normal distribution perfectly. And then to show an extreme case where we have a very unnormal or non-normal distribution to heights, I've made up the third column here. So I just tagged it or labeled it not normally distributed heights. So I'm going to be using this example here by comparing these 3 data sets to show you different ways that we can visualize and test whether our data sets are normal or not normal. So the first thing, here's the data set itself. So in the Excel spreadsheet, I'm just organize my headers because the labels are very long. So one thing that you can do when you have very long labels and you can't see it all is that you can use that data wrap. So you can get it into columns that are a little more narrow, a little easier to work with, right? So there I have my 3 data sets. So first I'm going to drag over top of my observed heights. So I should have 100 data points there. I'm going to go, first thing I'm going to do is make my histogram. Okay, there's my histogram. If I wanted to, but I just want to compare the histogram between these 3 data sets. So I'm going to give it a title, Observe Heights. So you can kind of see that it's pretty close, not perfect to a symmetrical normal distribution. I might want to do something else. I can go down here and see how much skew I have in this data set. So again, the expression skew, and I'm going to drag over top of my data. Let's see, I've got a slightly negative skew to this first data set. All right, so that's the first one, histogram for the first. A histogram for the perfect normal distribution. Back to my histogram. So there I can see that, right, much more symmetrical distribution in the histogram as I would expect for a perfectly normal distribution. So I'm just going to label this expected heights for normal distribution. And let's see what the skew is for this. It should be very close to 0. It's only 100 points, so it's probably not going to be exactly 0. Oh, so it's very close, a very slightly positive skew. All right, so let's do the same thing for the third column. And this data set, again, is a this is one quick way that you can see whether your data set is generally following a normal distribution or not. So let's just see what the skew is for this. Imagine it's going to be relatively large one way, right? Minus 0.17, so a very strongly skewed data set there. right? So here are my 3 histograms, right? The observed heights, right? So you can see again, close but not quite. There's a slight skewness to this data set here. There it is for my perfectly normal distribution, theoretical normal distribution, right? Very symmetrical. And there is my very non-normal frequency histogram for that third column. So a very different, right, shape of the histogram, of course, between the perfectly normally distributed and the non-normally distributed, with my observed height data set being closer to a perfectly normal distribution, but not quite. You can see there's a little bit of asymmetry going on there. So another thing we can do is use JASP to visualize our data, basically do the same thing. So I'm going to open up the CSV file, right? There's my 3 data sets right there. I'm going to go to my data descriptive tab, and I'm going to plunk in my variables, right? You can see that my descriptive tables starts to get populated. And then I can go down to my basic plots, and I can quickly make up my histograms here. So these are basically the same histograms. The size of the binning is a little different. So you can see, right, there's the third one. Again, very non-normally distributed. Then I can also, right, draw a line through it to get a better visualization of the symmetry or asymmetry. So I can see for the middle histogram there, you can see how symmetrical it is compared to the bottom histogram, which is all over the place. And then I can also go into my I can also visualize my data through box plots, right? So there's my first observed data set. There's my perfectly normal distributed data set right there with the median perfectly in between the box ends and the whiskers. And there's my very asymmetrical, non-normally distributed data set showing the outliers. I can also, if I want to visualize, I can add the violin and the jitter element. Maybe a little too busy there, so I'm going to take the jitter off and just keep the violin. It's kind of like drawing a line through the histogram. Another way to visualize this, whether it's symmetrical or not. So you can see with the histogram or the box plot right there, it's very symmetrical. Okay, so that's the first way we can see whether our data set is generally following a normal distribution or not, is just make up some plots, whether they be a histogram or a box plot. Another tool that we can use is called the quantile plot, or sometimes called the QQ plot. And what the quantile or QQ plot is doing, it's basically comparing, it's basically a scatter plot that's comparing the quantiles, the actual quantiles in your data set to what they should be theoretically for a perfectly normal distribution. And you can see that there's dots, right, in each of these scatter plots, and then there's also a straight line. Now, the idea with these quantile or QQ plots is that the closer your dots follow that straight line, the more normal your data set is. So the more divergence, the less normal your data set is. So we can also make up these QQ plots, quantile plots in JASP. So I've got my data set here. I click the QQ plot box, checkbox there. So for my observed heights, I can see there's a little bit of deviation away from the line there. For my perfectly normal distribution, as expected, the dots basically run right along the line. And then for my very non-normal distribution, I can see there's a huge amount of divergence of my points away from that theoretical line. So the idea, again, the closer that the dots or your scatter, right, line up against that line, the closer that your data set is to following a perfectly normal distribution. So you can also read these QQ plots to identify how your data set deviates from a normal distribution. So here we have a skewed left, right, or negatively skewed data set right here, right, where we have a tail to the left. We can see that that tail, if you have a negatively skewed data set, it's going to show up in your QQ plot like this, where you have the deviation at the lower ends between your theoretical quantiles, what they should actually be for a perfectly normal distribution along that line, you can see that the sample quantiles are much below that. So that's indicating to us that we're dealing with a pretty strongly left skewed or negatively skewed data set, and therefore may not be normal. Right, the opposite, right? If we have a skewed right data set, this time we're going to see the divergence off the line on the higher end of our quantiles. And then what if we have more of a platykurtic distribution with fat tails? So this red line is showing us what we'd expect for a perfectly normal distribution. We can see that we, in our data set, in our sample, right, our tails are outside that theoretical normal distribution. So the way that a platykurtic or fat tail distribution shows up in a QQ plot is that you generally get a good match around the middle of your data set with the outliers of the tails diverging like so. Right, so there's our skewness or fat tail on the left there for our data set. And there's the fat tail for the points on the right of the data set. So here's just a box plots, a histogram, and what the QQ plot looks like for these data sets. So you can see on the left series of plots here, we have a very positively skewed data set, right? A very long tail on the high end of our values. We show up in our QQ plot with a big deviation away from the point on the high end. Here we have more of a normal distribution, but we see that we're missing some points, right? We're missing our tails on both the left and the right side. And that shows up where we see the deviation just on the ends, on the very low ends and on the very high ends. Everything else within the distribution lines up pretty good with what we'd expect for a normal distribution. And then here we have a slightly left skewed data set, right? So you can see the skew down here. We have the divergence away from the line. You can also see that we're missing some values here where we should have some values on the high end, and that shows up as the deviation right there. So just some notes here, right? When you're looking at these QQ plots and how to interpret them, if you're dealing with a kind of a skewed to the left, right, data set, this is what it's generally going to look like in blue here, your data compared to the theoretical red line. By contrast, if you're dealing with a skewed to the right or positively skewed data set, it's basically going to be the inverse of the left skewed data set, right, with the points or your data points being below in the middle of the data set compared to the theoretical. If you're dealing with a too flat or platykurtic distribution, your points are going to follow this kind of pattern or divergence away from the theoretical red line. And then by opposite, if you have a too peaked, right, or leptokurtic distribution, it's basically going to be the opposite pattern compared to the platykurtic distribution. So that's how you can interpret your QQ plots and what they're telling you about how your particular distribution diverges from what you'd expect for a perfectly normal distribution. Okay, so basically we've looked at plotting, we've looked at QQ plots. Now we can get into some more formal ways to determine whether we're dealing with a normal distribution or not. So these are statistical tests, formal statistical tests with a null hypothesis and an alternative hypothesis. We'll be using mostly the Shapiro-Wilk in this course in the lab as well, but some examples of statistical tests that you can do to determine whether your data set is normal or not: Shapiro-Wilk, Kolmogorov-Smirnov, chi-square, or z-test. So those are 4 examples of these tests that you can use. And the advantage of these tests is that they give a more clear or cut and dry determination whether your data set is normal or not. Because basically before, we were just going based on visualization. So it's hard to make a determination whether your data set is normal or not, right? It can give us kind of a general idea. And then once we got a general idea, we can use one of these statistical tests to determine more definitively whether our distribution. So the two most well-known tests, the Kolmogorov-Smirnov and the Shapiro-Wilk test, right? Those are the common ones, right? They both use what's known as a null hypothesis, right? That states that the data that you're dealing with, your data set, is a normal distributed population or data set. So what is this null hypothesis, okay? And like I said, we'll be applying the Shapiro-Wilk test in the lab. But before that, in more general terms, what is the null hypothesis? So we'll be dealing a lot with null hypothesis further on in these lectures. So you can think of these null hypothesis, and it's symbolized by this H0 here, subscript 0. It's basically kind of like our default hypothesis, right? We assume it to be true, the null hypothesis, unless our statistical test tells us to reject it, right? So if our test tells us not to reject the null hypothesis, we just stay with our null hypothesis, which again is kind of like our default or assumption about our data set. So here's an example, right? So we do this, we use null hypothesis all the time in science, right? So maybe we're doing an experiment where our null hypothesis is that light color has no effect on plant growth. So maybe you do an experiment where you're exposing plants to different colors of light, but you're thinking, it probably doesn't have any effect on plant growth. So that's going to be your null hypothesis. It's only when you do your experiment, you collect your data, you analyze it, you do your statistical tests, right? If that test tells you to reject the null hypothesis, that means that when you reject it, you're saying, oh, I'm going to go with my alternative hypothesis, that light color does affect plant growth. So it's going to be either sticking with your null hypothesis or failing to reject it. And if you do reject your null hypothesis, you have to go with your alternative hypothesis. Experiment that you clearly define before you do your actual experiment, what your null hypothesis is and what your alternative hypothesis is. So here's just kind of a funny example here, right? Did he brush his teeth or not? Or alternative hypothesis that he did not brush his teeth, the data, dry toothbrush, rejection of the null. Okay, that went by a little fast. But so we have size that's greater than 50. Usually we're going to go with the Kolmogorov-Smirnov test. Okay, let's get back to talking a little bit about the Shapiro-Wilk test. So we can do the Shapiro-Wilk test in JASP. I'm going to open up my data set here. I closed it, so I'm going to have to reopen my lecture 6 height data, CSV. Okay, let's enter my variables again. And then to run the Shapiro-Wilk test, just going to show you the table here. Go to the left a bit. To get back, there we go. So I'm going to go down under the statistics tab, pull down menu. I'm going to go to under distribution. I want to see my skewness, kurtosis, and I'm also going to click the Shapiro-Wilk test. So you can see as soon as I click those buttons, it populates those variables in my descriptive statistics table. Okay, so this is the table here, right? And these are the three corresponding histograms, right? My observed heights is here. My expected normal distribution is that one. And then my very non-normal distribution is on the right there. So in the Shapiro-Wilk test, what you're going to get back is two main numbers. One is the test statistic itself, here just called the Shapiro-Wilk. So you can see for the observed heights, which is not quite normally distributed, not perfectly, I get a test stat for the Shapiro-Wilk of 0.986. For my perfectly normally distributed data set, I get a test stat back of 0.999. And then for my very or non-normally distributed data set, I get the lowest test stat back, 0.822. So you can see as your data set is more perfectly normally distributed, the Shapiro-Wilk test stat gets closer and closer to 1. The second variable, and a very important one, is what's known as the p-value. Okay, so you can see down here now, the p-value for the first data set is 0.373. For the perfectly normally distributed data set, it's 1. And then for the very non-normally distributed data set, it's very small. It's less than 0.001. So you can see there's a lot bigger difference in the numbers for the p-value compared to the Shapiro-Wilk. So often we want to use this p-value to determine whether we're going to consider our data set to be normally distributed or not. So again, in the Shapiro-Wilk test, right, we're going to set up our null hypothesis H0, in which the distribution is considered to be normal. If we decide to reject that null hypothesis, we're going to go with the alternative hypothesis HA, in which we're going to assume that the distribution is not normally distributed. Right, so the idea is that we always assume that the null hypothesis is correct, that our data is normally distributed, unless our statistical test, in this case the Shapiro-Wilk test, tells us to reject that null hypothesis and go with the alternative hypothesis, in this case that our data set is not normally distributed. So again, the advantage of these statistical tests like Shapiro-Wilk is that they give us a definitive answer whether we can consider our data set to be normal or not normal distributed. So there's a couple ways that we can do this. And the main way we're going to look and decide whether we're going to retain the null hypothesis or reject it is that we're going to be comparing that p-value that we saw in the tables there to what's known as a critical value. So just note that that critical value that we're comparing the p-value to is sometimes referred to as the alpha value. So it's by this comparison between our p-value and our critical value is that how we're going to make the determination whether we're going to retain the null hypothesis or not. And this is kind of the rule right here. So the rule here is that if the p-value is less than alpha, our critical value, we're going to reject the null hypothesis that the data set is normal, and therefore go with the alternative hypothesis that our data set is not normally distributed. So let's put this in the context of our Shapiro-Wilk test, right? We reject the null hypothesis of normal distribution if our p-value is less than the chosen alpha value or critical value. If our p-value is greater than our alpha value or our critical value, then we're going to fail to reject the null hypothesis. Basically, fail to reject the null hypothesis means that we're going to keep with the null hypothesis, and therefore we're going to consider that our distribution of our data set is normal. So it basically comes down to this, right? So when our p-value is greater than alpha, we stick with our null hypothesis. When the p-value is less than or equal, we're going to go with our alternative hypothesis. See that? It's basically, this is kind of the way we make the decision, looking at the p-value to see whether it's either greater than the alpha or it's less than or equal to the alpha. Right, same kind of idea here. When we're making our decision in our Shapiro-Wilk test, is our p-value smaller? In this case, we've chosen an alpha value of 0.05. So we can choose any critical value we want, aka alpha value. A lot of the times we select 0.05, and we'll get into why we select 0.05 most commonly in a bit. So if the p-value is smaller than 0.05, if that's not true, we keep with the normal distribution assumption. If our p-value is smaller than the alpha value, in this case 0.05, we're going to reject the null hypothesis and assume that our data set is not normally distributed. So again, like I was saying, these critical values, often we pick the 0.05 value, but we could pick any value we want. We could set it to 0.01, we could set it to 0.1, we could set it to 0.2 if we want, right? So by setting this critical value, we make it either harder or easier to reject the null hypothesis. So you can think of the p-value. If the p-value is smaller, right? Remember area underneath the curve, right? If the p-value is smaller than the critical value, or aka the alpha value, that means that we're likely going to reject the null hypothesis. So again, right, think of the alpha value, the critical value, as kind of the threshold that the p-value has to be smaller than in order for us to reject the null hypothesis. If our p-value is greater than the critical value or alpha value, right, we're going to fail to reject the null hypothesis, and we're going to keep with the idea or the assumption that our data set is normally distributed. So really what the alpha value is telling us, say if we set an alpha value of 0.05 in the Shapiro-Wilk test, this means that there's a 5% chance that the Shapiro-Wilk test is wrong. In other words, there'd be a 5% chance that we would wrongly reject the null hypothesis. But say if we set the alpha to 0.01, so a much lower alpha value, a higher threshold, that means in this case that there's only a 1% chance, right? If our p-value is less than an alpha value of 0.01, there's only a 1% chance, right? 1%, 0.01. There's only 1% chance that we would reject the null hypothesis incorrectly. So the lower that we set the alpha, right, the lower the chance that we're going to falsely reject the null hypothesis. So back to our height data sets here. So let's look at what we're dealing with here. With our middle data set, our perfectly normal distribution data set. For our p-values, we have a p-value of 1, right? Of course, 1 being much greater than 0.05. So in this case, right, we're not going to reject the null hypothesis, not even close, and we're going to maintain our null hypothesis that our data set is normally distributed. But this is what we expected, right? Because I set it up that this is basically a very close to perfectly normal distribution. So no big surprise here that we have a very high p-value, and therefore we would not reject the null hypothesis. What about our in-between case? So for this data set here on the left, we have a p-value of 0.373, still a lot larger than 0.05. So just like with the perfectly normal distribution, we are also, even though it's not, right, it's not perfectly normal distributed, it's not over the threshold because the p-value is greater than 0.05 to reject the null hypothesis. So we would still maintain that this, based on the alpha value of 0.05, are dealing with a normal distribution, even though it doesn't really look like it based on the histogram. Let's go to our third data set here. In our third data set, we have a p-value which is less than 0.01, which is, right, less than our alpha value of 0.05. So because our p-value is less than 0.05, right, we set our alpha value at 0.05 in this case. because the p-value is less than it, we, in this case, are going to reject the null hypothesis and therefore assume that we're dealing with a non-normally distributed data set. So again, this is how you use the p-value of a Shapiro-Wilk test to determine whether your data set is normally distributed or not. Okay, so second part of this video is going to deal with inferential statistics. So far in the class, we've been dealing with descriptive stats, right? Mean, mode, median, things like that, standard deviation, coefficient of variation, basically describing the central tendency and the amount of spread of our data set. Now we're going to move into inferential stats, where we're basically taking a sample and we're seeing how well that sample represents the characteristics of the larger population from which the sample was taken. Right, so purposes of descriptive stats, right, kind of summarize, organize, visualize your data, right? Inferential stats, the purpose is quite a bit different, right? We're trying to insinuate from those samples what the larger population characteristics are. And we're also doing hypothesis testing and making predictions from those samples. And basically what we're doing is trying to see how well our samples characterize characteristics of the larger population. So basically what we're using samples for, because of course we cannot go out and measure everything in the universe, we have to take subsets or samples and make inferences from those samples to the larger population. The question is, how well do those samples represent the larger populations? So how we choose our sample is very important. So of course we want a sample that represents the larger population as close as possible. We want to minimize the error, right? All samples have error, but it's whether our error is minimal or acceptable enough that we can make some inferences. And we want to avoid bias in our sample. We want to try to avoid sampling areas or groups that are not representative of the larger picture of our population. So some terms here, right? Basically what we're doing is we're gathering a sample and we're trying to see if we can represent what's known as the target population with our sample, right? So there's our target population. This is the thing that we're trying to measure, but because of logistics, time, money, right? We cannot go out and survey everything in this target population. So we have to rely on a small subset of measurements. This is called the sample. The problem is that every time we take a sample, because again, it's a subset, the sample does not perfectly look like the larger target population, just due to mathematical sampling error, right? Because you're taking a subset, the sample that you end up with looks different than the overall target population. What we're trying to do is reduce the amount of error, so what we get in the sample is representative of what's going on in the larger target population. So I've been using this term population. That just doesn't, it's not restricted just to like surveying people, humans, things like that. It can deal with physical things as well, right? Elevation. It's basically, in this case, population refers to kind of the whole universe. Basically everything that you're trying to measure, of which you can't. So you're trying to use a sample to represent that larger target population. Right, so it can be humans, it can be objects, right, from which the sample is selected from, right? You can kind of also think of it as the theoretical complete amount of measurements, possible measurements that could be hypothetically be recorded, right? So basically, in other words, the population is the thing that you're trying to measure, but because it's too large to measure completely, you're relying on a sample to characterize it, right? So sometimes we can get significant sampling error, what's known as sampling error, right? Just due to random selection, right? So here's our target population, Imagine we go out and randomly select, right? For, in this case, 4 of the people from the population, but it could be rocks, it could be fish, it could be anything, right? You can see that our sample is biased, right? Because it's not representing proportionally what is in the overall population. So therefore, we get some sampling error. And it's important to keep in mind that all samples contain error. And what we're trying to do is minimize the amount of error contained in our samples. So one common thing that we're trying to characterize, right, is that we're trying to characterize a population mean, remember this mu, right, by a sample mean, x bar. And we're trying to get a sample mean, which is as close as possible to the overall population mean. Right? So every time we go out and take a sample, right? So here's our target population. Here's a representative sample where it does a good job of, in our sample here, kind of characterizing the big picture within the target population. But what if we took a sample from this section of the population? We can see that we get a big difference between what's in the sample compared to what's in the population. So we're going to get a large sampling bias, and our sample is going to be misleading in terms of what's going on in terms of the overall actual target population. So here's a good example right here. Here's our population made up of different colors, right? So imagine we just take one subset, our sample right there, we can see that the result in terms of the proportions of purple and different colors, right? We completely miss the brown individuals there. If you're just looking at the sample, you'd think that the target population was 90% of the purples, right? But basically it's underrepresenting the blues and completely misses the brown. So here's a good diagram to show you how every time you take a sample, it gives you a different snapshot of what the overall population is. So again, here's our overall population, maybe just using the example of heights, right, with our mean of the population being right there. And these down here are 20 individual samples, right? I think 10 points taken out for each sample. And you can see that there's our X bar, or our mean. So remember, our sample mean is X bar. So all of these colors, right, are indicating the sample mean, the X bar. You can see there's a big difference in the X bar from sample to sample, and they're all basically off, except for this one down here. There's a substantial difference between each sample mean to the overall population mean. So here's this illustration, right? If we collect 10 points, it looks a lot different to 100 points. Now we have 1,000 points, 10,000 points, right? So as we get our sample size bigger, right, we tend to get a better chance of better representing our overall population, right? You can see a small sample size there. As the sample size gets larger, it starts to approximate the overall target population better. Here's another diagram, right? So imagine this is our population. This should actually probably be a smooth, imagine this is a nice, smooth, symmetrical normal distribution, and the population mean is right there. And here's samples of different sizes. So a sample of 20 points, sample of 100 points, sample of 500 points. We can see that, right? The different samples of 20 individuals, right? We can see there's a lot larger movement back and forth of the median or the mean or whatever, compared to if you have a larger sample size. And there's less movement, it's more stable once you get to a larger sample size. So usually we get the largest sampling error when the number of values that we collect in our sample is lower compared to higher number of values in our sample set. So another, basically the same idea, right? Here's our population on the bottom here. Say this is the, I know it should be the median. Let's just say we're trying to collect or describe the median of this population data set. If we collect only 10 points, we can see that there's a lot of back and forth, right? We get a lot of differences between each sample. as we start to increase the sample size, we see that it becomes much more stable. There's a lot less error. There still is error, but there's a lot less error as we increase our sample size, aka Rn. Right, so the goal here is that we're trying to collect a representative sample in which we're usually trying to estimate the mean of the population by the mean of our sample, X bar, okay? But the error of our sample is dependent on the characteristics of the sample, right? For one, we just saw the number or the size of the sample indicates or affects the size of the sampling error. So we can change the sample to try to reduce amount of error by changing the sampling strategy, right? This affects something that's known as systematic sampling bias, which we'll talk about in a bit here. And like I said, we can also change the sampling size. Generally, as we increase our sampling size, we reduce the mathematical error between our sample mean and our population mean. So a couple things here, terms here. One is called, we already gone over sample size, right? That's basically our N there. Another thing is our sampling bias, right? Where we take the sample from can have a big effect on what the sample looks like and how either representative or unrepresentative it is compared to the overall population. So you can imagine, right? Imagine you're trying to measure the weight of fish in a lake. An example of sampling bias would be to go to one bay and just measure fish from there, right? Only measure fish from one geographic location, because those fish, right, might, because they're all in one location, might not be representative of all the fish in the lake. So that would be an example of kind of a geographic or spatial sampling bias. So here's some more examples of sampling bias. Imagine this outer rectangle is our target population, which we're trying to get a sample of, right? Here's our sample population. That's referred to as under coverage, but our samples are usually always under coverage, right? Because usually we do not have over coverage because, right? Because usually the sample is a subset of the larger target population. Kind of a interesting anecdote about sampling bias is how you set up your methodology, right? So imagine now these people here are sending out a survey, and the survey basically asks them whether they, yes, I love responding to surveys, or no, I toss them in the bin. Well, guess what? Your results are going to be based on just how that survey is set up, right? Only people that like surveys and send them back in, right? So you're going to get a high result that people love surveys, right? But maybe the overall actual results are much different. So that's another way that you can bias your sampling protocol. Right, so we got two things here. Sampling error occurs in all samples. Remember that all samples are imperfect representations of the larger population. And then we can quantify this sampling error. One way we can quantify it is something that's known as the standard error. And that's the mathematical quantification of how much the sample, say, mean deviates from the population mean. Right, some sources of sampling error is, one of them is unusual events, right? If a random sample only observes, right, an unusual occurrence, right, you go out and sample some strange portion of your data set, right, maybe at a strange time, right, you're going to get a sample that's very unrepresentative of your overall population. It's going to misrepresent what's going on in the overall population. Another thing that affects sampling error is the inherent variation in your population. If you have a population, say for, again, let's go back to heights. If for some weird reason, your population all has people with very similar heights, your sample is likely going to have less error compared to if you have trying to measure a population where you have a large variation in heights. Right, so one of the things that we're trying to do, right, is we're usually trying to estimate, again, mean and things like standard deviation, basically our central tendency of our population and how dispersed it is. So mean and standard deviation are two metrics that we're usually trying to use a sample to estimate the mean and standard deviation of a larger population from, right? But we usually never know what the actual mean and standard deviation of the population is. That's why we're using a sample. But we can calculate what's known as a margin of error to quantify how the difference between, say, our sample mean and our overall population mean. And one metric that we can use this is commonly used is called the standard error, SE. Okay, so the standard error is a measure of the sampling error. And basically how it's calculated is two things. It uses the standard deviation of the sample, here S, and the number of observations in the sample. So the standard error, right? So this tells us how different or how off our sample, say, mean is going to be to our population mean. We take the sample standard deviation divided by the square root of our sample size n. And so this standard error basically quantifies mathematically the error between our sample and our population. So a couple things are going to affect the size of this mathematical error. Again, the larger the sample that we take, the higher the n, usually the smaller the sampling error is going to be. Again, because if we go back to the standard error, we can see that if we start to increase n here, that's going to decrease the SE, the standard error. Also, what's going to affect it is if our standard deviation of the sample is smaller, meaning that there's less variation out there. So as the standard deviation of the sample decreases and the sample size increases, we get a smaller and smaller standard error. Right, so again, a big thing is the sample size. The larger the sample is, the more likely that or the less amount of sampling bias you're going to have within the sample itself. Okay, so that's it for this lecture. So the practice midterm, there's no quiz this week, but the practice midterm will open up at 11 o'clock this morning. So you have 2 weeks up until the day of the midterm itself to take a look at that. So have a look at that and have a good winter break. Keep warm next week. And I will see you next Tuesday. So the Tuesday after this one for Lab 4. But of course, get a hold of me if you have any questions. Really important to take a look at that practice midterm. Usually it's a big help in helping you prepare for the midterm. Okay, have a great winter break, and I'll see you on the other side of that.